Moving into sorting gets us a couple of really great advantages here. We can start to understand some of the more complicated algorithms, not the most complicated by any means, but more complicated as we're getting deeper into computer science and programming. It also opens up a whole new realm of functionality as we discover new aspects of how to design and build code. So I want to distinguish between searching versus sorting here. We've talked a little bit about searching in building heaps and then some of the other exercises we've done beforehand. But searching is kind of like looking through the skyline here saying, can you find this building? Just finding something in the list, I can ignore a bunch of them and just find the one I'm looking for. If you're looking for a house, I don't care about everybody else's houses on the block. I just need to care about the one I'm looking for. Where sorting, like the bottom list here, is I need to take each one of these, in this case, buildings, and put them in order of height. And that's a little bit more work because I got to consider each and every single one of them. If I optimize my data structure, like we talked about with priority queues and heaps, and you also talk about within trees and maps, and using hashing structures, I don't need to see everything. I can leave most of the items out and just jump to the ones that are most interesting to look at, most relevant. But in sorting, I typically start with some sort of unordered data structure, a list or an array, and I have to consider basically each and every item relative to each other. The list is only sorted when every item is in order in that list. So here's an obvious, somewhat example of what I mean by that, but it's worth going through obvious examples just to make sure we all understand where we're coming from. So if I was going to sort this list, I need the list to be starting with the lowest item on the list and then going up to the highest on the item on the list. So if I look at this, A, B, C, D, E, F. F is the first level letter I hit, then G, H, I, and then so on and so forth. So inevitably, this sorted list looks like this. So it's a nice little, mixed word jumble, if you will. But sorting fun becomes Fidginor's two. Not that we're actually reading the list like that, but that's the idea. That's the goal of sorting, is to put it in the order. Now, everything we're going to be talking about is going to be sorted lowest to high. So that's a couple of the assumptions we could talk about throughout this entire section of talking about sorting. The values have to be ordered in some way, and some of those are natural. So numbers and letters. We have low numbers and high numbers. We have A comes before B comes before C. We have ways of sorting strings the same way, starting with first letter, second letter, and so on. Um, so everything that we're going to talk about is going to be sorted lowest to least to greatest. You could do greatest to least just the same way, and to some degree it doesn't matter, because if I have an array, I can just as easily sort the array, from the length minus one down to zero as I can from zero up to length if I'm printing everything out. A linked list, obviously there has an order of dependency inside of that, but you can also make a doubly linked list, and that doesn't necessarily matter either at that point. But most of the time, we're also basically going to be using arrays across the board here as well, just not a reference. They can be used in other data structures, but we're just dealing with arrays. Um, the other thing is we are assuming it is some reorderable data structure. So as I said, I can exchange two values and the order still means something. I can't sort a set. Some sets are naturally sorted. Trees naturally sort a set. Maps do not. If I use hashing and hash maps, they don't use a natural order to things. So again, our focus is just on arrays, but theoretically we could use a linked list or something like that as well. So this whole idea of comparison comes to the question of, what if I don't have a number or a string? Well, for instance, dates. You can think about maybe the clock problem. You worked on the clock problem in this class. You could talk about the clock problem as being hours, minutes, and seconds. That's a complex object, but there's some rules that says there's an ordering in which I look at things. I look at the hours the same, then the minutes the same, then the seconds the same. In this case, we have trees. So let's say I wanted to order some trees. Well, I can figure out some rule by which I order the trees. Perhaps I order trees based off of their height. basically, maybe I do them by their width. Maybe I do them by their age. Maybe I would do them by the number of leaves they produce. Maybe I do them by some sort of indexing system that some tree society has built. There maybe have an ID for each different type of tree, and there's just some the order doesn't mean anything, but it's just associated with a tree. It actually doesn't matter. I could do trees by complicated formulas like our clock problem, one, then the other, then the other. So the trees that live in forests versus trees that lives in plains versus have each of them be sorted in different ways. So I do forest trees first, and then I do deciduous versus jungles. Then I do the amount of leaves to produce, and then I do the height or something like that. I mean, it doesn't matter. The point is, as long as there's a consistent way of comparing and evaluating these trees, I can sort them in that order. And then sorting of lists might change based off of the comparison that I'm going for. And so just know that sorting is always going to be based to the quote unquote key by which I'm sorting on. I could sort trees by height. I could sort trees by their age. I could sort buildings by height. I could sort buildings by how expensive they are, or what's their occupancy, or how old the building is. Any number of these things, and each of those lists are going to be slightly different. So just know that sorting is not always a one size fits all, even on the same data. So then it comes into the question of how do we choose the appropriate sorting algorithm? This section we're going to deal with, I mean, at least more than a handful. I can think of 8 or 9 algorithms we're going to look at straight away for sorting. And it's a trade-off in sorting all the time of speed versus memory. You can also say complexity, but complexity is a developer issue. And so really, we mostly choose these by speed versus memory. And for developers, if you don't want to do a complicated sorting algorithm, you just reuse an existing one. But speed being is how quickly does it get done, or more importantly, how few calculations does it have to do to get there? Time is definitely normally the measure of that, but you could also talk about the number of calculations. Time can be a little bit of a misnomer because you'll see in the next few weeks how easily time is fooled based off of interrupts and other processes and whatnot. So the same algorithm might perform differently in different time situations, but we'll come back to that later on. But speed is definitely really important. But sometimes the way I speed things up is by using more memory. And so there are some of these algorithms that make a copy of things and then reinsert them back in later on. It speeds them up dramatically, but it also means that you have to, if you have a very long list, you have to have double or at least some fraction of that memory available to you. And some applications are really tight on memory, and speeding it up is less important than keeping memory under control. So there's some trade-off right there. Now, to be fair, there are a few of these algorithms that are just fundamentally better than the others. So you might say to yourself, well, why do I have to study all of these silly sorting algorithms? Why do I have to do each and every single one of them when some of them are clearly better than others? Well, part of that is it gives us a little bit of a lens into looking at the performance. It gives us a way to be able to study about what performance of algorithms looks like in a number of known algorithms. If you're going to do sorting, you're probably going to use an existing sorting algorithm. You're just going to call that, be done with it. Heck, a lot of the sorting is done in databases long before you ever even load it into your system for large data sets at this point. But yeah, there are going to be times where you sort things. You're going to call and choose a sorting algorithm. And there's also going to be times where you need to understand which algorithmic choice you have is the best. And so sorting lets us look at choices like how many number of operations happen. So let's say we have this little town here and we have a mail person that's going to be driving around the town. So the mail stops, delivers a package, and then goes to the next spot and delivers a package, and then goes to the next spot and delivers a package. And then you realize all of a sudden they're backtracking all around town. And so the number of operations is basically a way of how do I not backtrack? How do I not go to places that I don't need to go? Either by doing things in a logical order, so that way I don't have to, driving around, drive down the same streets more than once, or doing it in a illogical order, but actually nets a a faster speed. Like you might think the best way to sort is two items next to each other, and we're going to see a lot of algorithms that that's not the case. By tweaking it around a little bit, we can actually do some really great things to improve our speed. So another aspect of why we want to study these algorithms in such detail and work on them, even ones that we maybe wouldn't use in a real world situation, is to expand our mind for future problem solving. We really want inspiration of different types of algorithms and how the algorithms solve different types of problems to remind us of ways to solve problems when we come across them in the future, and also perhaps remind us of better ways to solve problems. We might start to build something that looks an lot like a bubble sort. And we realize, like, oh yeah, if I tweak this, there's a better way to do this. There's a faster way to do this. And that's the types of things that I think it's really valuable. And one of the reasons why I think it's really worth studying even algorithms that have shown to be much slower than others, because it reminds you of when a similar algorithm might not be the best one to use and might jog your memory about a better way to solve that type of problem. So let's take a look at these. I hope you enjoy this section. I think it's really quintessential programming, computer science type work, but it really should expand your skill set and knowledge base as a programmer as well.